Swayam Prabha. Digital India. Educated India.
Hello and welcome back once again to this lecture series on aluminum based alloys and metal matrix composites. So right now we have been discussing about precipitation hardening in aluminum alloys, and with regard to that we have seen that the precipitation occurs in a particular sequence. The exact nature of this sequence depends on the alloy, but generally the sequence is as follows. So once it is solutionized, that is when it is heated to a high temperature and then water quenched, a supersaturated solute solution forms. We have seen that, right? And then when it is aged, it goes through a particular sequence for forming the strengthening precipitate, okay? And that sequence is as follows. The supersaturated solid solution, then we have formation of the GP zones, which are nothing but cluster of the solute atoms forming on particular planes, and after that the strengthening precipitate forms, followed by formation of the equilibrium phase. So this is the sequence which is generally found in aluminum alloys as far as the precipitation hardening and the formation of the precipitate is concerned. So with respect to this sequence and the precipitation behavior, we have seen two alloys in the previous lecture. First, we discussed about the precipitation sequence in the 2000 series alloys, that is the aluminum copper alloys, and we have seen what is the precipitation sequence in these alloys. And after that, we had seen the precipitation sequence in the 6000 series alloys. So in this lecture today, we are going to continue on it and see the other aspects of precipitation hardening and also the other precipitation hardenable alloys as to how the precipitate forms and what kind of precipitates are there in other edge hardenable aluminum alloys. Okay, so this precipitation sequence that you have in the 6000 series alloys, this will occur when the aging is done in a particular temperature range. Which is 170 to 200 degree Celsius. Because for this particular alloy, the GP zone solvers, which is the temperature beyond which the GP zones will dissolve, is around 225 degree Celsius, right? So that is why it has to be done below that in this particular temperature range, okay? Typically around this 170 to 200 degree Celsius. And this precipitate will form for a particular ratio between magnesium and silicon. which is around 1.73:1. Some cases there may be little excess silicon, and that will in fact give rise to higher strength but low corrosion resistance. So let's take an example of an alloy in this series. And 6061 is a very popular alloy in this particular series. This has a composition of 1% magnesium, 0.6% silicon, and some amount of chromium. And this is used in T6 condition, that is artificially aged to peak hardness. And in this condition, it gives a yield strength of 275 MPa. Okay. So you can say that these are intermediate strength level aluminum alloys. The strength is higher than the non-heatable alloys, but lower than other heatable alloys. Okay, so it is somewhere in between, and they are used in architectural applications. Where some strength as well as good appearance is needed. Good surface finish is required in this kind of applications. And in order to improve the machinability, sometimes a small amount of lead and bismuth can be added. And when you have presence of lead and bismuth, that alloy in fact becomes 6262. So here, apart from aluminum, magnesium and silicon, you also have some amount of copper and some bismuth and lead. And little chromium also, which is good for grain refinement because it inhibits the grain growth. These alloys can be easily formed into complex shapes, and extrusion is a very commonly used process for shaping such alloys. And their quench sensitivity is also low, and therefore they can be directly quenched from the extrusion temperature. That means these are used in T5 condition. Right, if you remember, the T5 temper is quenching from a high temperature manufacturing process, which is extrusion in this case. This 6062 is also used in T9 condition, which is solution treatment plus artificial aging followed by cold working. And in that condition, it can give a proof strength of 380 megapascal. And alloys like this 6061, 6063 can also generate very good surface finish. And in fact, they can be given different colors by anodizing. Anodizing is a surface treatment operation for aluminium and their alloys to generate different kind of colors on the surface. And these kind of articles can find applications in different places where the surface finish or the surface appearance is of importance, for example in architectural applications and things like that. But for this to occur, for different colors to be given, the impurity content should be as low as possible, because that might affect the anodizing operation. Next, we have the 7000 series. The aluminium, zinc, magnesium alloys. Here the precipitation sequence depends on the magnesium to zinc ratio. In most of the commercial alloys, the zinc to magnesium ratio varies from 5:2 to 7:1. And the precipitation sequence in that case would be as follows. Here the main precipitate is the eta prime phase and the equilibrium phase is eta or MgZn2. If you look at the GP zones, in this case also they are spherical and they start with zinc cluster, and slowly the magnesium atoms join. And then this transform to plate shape on 111 planes. As the aging is continued, it will increase the diameter of the plate, but the thickness will remain more or less same. Now let us look at the precipitate, that is eta prime. These are also plate shaped. Forms during high temperature aging. And finally, on continued aging, this equilibrium phase eta forms. Which has a hexagonal crystal structure. So here again, the precipitation behavior would depend on the composition, particularly the amount of copper. This series has got high strength when copper is more than 1%. So if it is, within 1% or less, then it actually remains in the solid solution and does not take part, the copper does not take part in the precipitation, and therefore you may not get the strengthening. But as you increase it beyond 1%, the copper atoms will go to the GP zones. And it also increases the solver's temperature for the GP zones, which means that it provides a greater thermal resistance to the GP zones. And of course, as the aging continues, the copper atoms also join the precipitate that forms. And also gives rise to a significant improvement in the stress corrosion resistance. And in order to form the precipitates uniformly, it is necessary to form the GP zones first. So there are chances, depending on the conditions of aging, that the precipitate can form directly from the supersaturated solid solution. Okay, so in that case, the precipitate may not form homogeneously. Okay, and in order to make sure that it forms uniformly or homogeneously, it is necessary that the GP zones form first. Aging temperature for the 7000 series alloys is typically in the range of 115 to 130 degrees Celsius. And a very popular alloy in this series is the 7075. This alloy has 5.6% zinc, 2.5% magnesium, 1.6% copper, and some amount of chromium. And this is used in T6 temper. And the T6 temperature for this is 120 degrees Celsius, the aging temperature. And the aging time is 24 hours. So if you age it at 120 degrees Celsius for 24 hours, you will get the peak hardness. And the precipitation sequence depends on the quenching rate. If the quenching rate is slow, then the precipitate will form directly. And they'll form preferentially on dislocations and grain boundaries. And in this case, the number of vacancies will also be less because it is cooling down at a slower rate. So the vacancy concentration is reduced in this case. And therefore, the GP zones will form at a lower temperature. In such a scenario, when the vacancies are less, the GP zones can form homogeneously at lower temperature, such as 100 degrees Celsius or so. So in order to make sure that the GP zones are forming homogeneously, because that is a requirement for the homogeneous formation of the precipitate, as I said before, what is done is a two-stage aging is done in this case. In the first stage, the GP zones are formed. And once the GP zones are stabilized, the temperature is further increased for the precipitation to occur. A typical two-stage aging could be as follows. First, aging at 120 degrees Celsius for 1 hour, followed by aging at a higher temperature, around 160 to 175 degrees Celsius. Okay, so this is just to make sure that we have enough GP zones forming so that the precipitates can form uniformly. Okay, so this was about the 7000 series. We'll talk about a little more on this, taking an example of a particular alloy. And with that, we come to the end of this lecture. Thank you for your attention.